Welcome, everyone. You are joining us for the Laser-Driven Light Source, Theory, Practice, and Applications. This webinar is presented by Hamamatsu Corporation and hosted by Photonics Media. Today, you're going to hear from Dr. Slavomir Piatek, a senior university lecturer on physics at the New Jersey Institute of Technology and a science consultant for Hamamatsu Corporation. In this session, he is going to talk about the operating principles of the laser-driven light source, its optical characteristics, and applications. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access a recording of this webinar online after the event, and you will receive a link to that recording in your email inbox. So with nothing further from me, I'd like to welcome Dr. Piatek. Welcome.
Thank you, Joanna. So let me just set myself up a little bit here. Okay, so again, first I would like to thank everyone for attending our 1 hour long webinar, which is sponsored by Hamamatsu Corporation. Again, I'm Slavomir Piatek, and I'll be with you for the next 1 hour or so discussing laser-driven light source. The presentation is divided into 4 parts. In the first part, I'm going to discuss some basic definitions and characteristics of light, generic light. In the second part, I'll discuss well-known broadband sources of light. These are the sources that you are absolutely aware of. They've been in existence for some time. In the third part, I'll discuss a relatively new source of light, which is laser-driven light source. So here we'll discuss the basics of its operation, physics, the design, some limitations, and various variants of that source. In the fourth part, I'll discuss some applications of these laser-driven light sources, and I'll also contrast and compare this particular source with the existing broadband sources. So let's start with the definitions and characteristics, so a little bit of physics. So suppose I have a source of light of certain area, and I'm an observer. I would like to specify the light that this source emits at my location. There are various ways to do that, but the one that is particularly useful is spectral radiance. So please note that I can divide the source into tiny little elements of the surface, dA, and each surface element, or I should say its normal or projection with respect to the line of sight, is going to emit certain power, d phi, per unit area, per unit steroradiant, and per unit of wavelength. So therefore, this quantity, spectral irradiance, is color or wavelength dependent. If I wanted to find the total power that I observe at this point, then I would have to integrate over the entire area of the surface and also integrate over the spectrum of this source. And that would give me what's known as bolometric power. So let's now go on the receiving end. So in the previous slide, we talked about emission of light, but now suppose I'm at some location, some distance away from the source of light, and I would like to quantify the light I am receiving. And so one quantity is known as irradiance, and this is a measure of how much power I get per unit area. If I wanted to know the total power received by this entire area, then I would have to integrate that irradiance over the area. However, if I do care about which wavelengths of light contribute to irradiance, then one can talk about spectral irradiance. So it has similar units as irradiance, except that we have per nanometer. So these two are in fact related. If I were to integrate spectral irradiance over the spectrum, then I would get the quote unquote irregular irradiance. Another very important characteristic of any source of light is its spectrum. So fundamentally, spectrum represents wavelengths of light that contribute to the overall light. Also, the amplitude of, for example, spectral irradiance will tell me how much a given wavelength or range of wavelengths contributes. On this slide, I have three spectra that correspond to the same hypothetical source of light. On the left-hand side, you see spectral irradiance as a function of wavelength for a source of light where the spectrum is flat. However, there are a number of ways of representing spectral irradiance in different units, and also wavelength. Instead of wavelength, I could use, for example, photons energy. And so in that case, the shape of the spectrum is going to change. So for example, in the middle, you see spectral irradiance, but in different units as a function of photon energy. And the shape of the spectrum is somewhat different, even though it represents spectrum of the same source of light. Probably the most common way of representing spectrum is the one shown on the left-hand side. But please be aware of these subtleties when looking at spectra or when comparing spectra in different, for example, publications or different representations. Another important aspect of light is temporal and spatial coherence. Books can be written on this topic, but here in this short webinar, a brief introduction. Suppose I have light coming from the left, represented by wavefronts, and I'm at certain location. By temporal coherence, we mean the time elapsed during which the wave or light resembles a sinusoid. So if I have, for example, monochromatic light, which means it's represented by a single sinusoid with certain wavelength or frequency, then temporal coherence is infinite because I see sinusoid for infinite amount of time. If I multiply that temporal coherence by speed of light, then we talk about coherence length, longitudinal coherence length. There's also so-called spatial coherence. In this case, I select 2 points in space and I look at phase relationship of impinging radiation for these 2 points in space. So for example, if the phase changes exactly the same, then there will be a spatial coherence between these 2 points. As I will show you shortly in the next slide, that spatial coherence effectively depends on changes in the shape of the wavefronts that represent light. One can test how much temporal coherence we have in a given source of light, for example, using Michelson-Morley interferometer. We have a source of light. The light is broken into 2 paths. One goes towards mirror M2, which is stationary. Other one goes into mirror 1, which can be moved. The 2 lights are then combined and allowed to interfere. If the source of light is perfectly monochromatic, as I move the mirror, I'm going to go through minima, maxima for any distance d. However, if the light is not monochromatic, if there is a finite coherence time and thus finite coherence length, then after moving mirror by a certain distance, the interference pattern is going to disappear. One can show that the coherence time or coherence length is inversely proportional to the bandwidth of the spectrum of the source of light. In this presentation, we'll talk about broadband light sources which have broad spectra, and those sources will indeed be characterized by short coherence length, which can be used to one's advantage in certain applications. Let's now look at spatial coherence. Again, this is a phase relationship for points in space, and one can talk about so-called spatial coherence area. So how much area on the wavefront is coherent, and one can show, interestingly, that this spatial coherence area is first, let me start, inversely proportional to square of the size of the source. So if the source of light is a point source where s is equal to 0, then regardless of distance from the source and regardless of the wavelength, there will be a perfect spatial coherence. However, as the equation shows, that coherence also depends on the distance. So in other words, if the wavefront is distorted as here, but with distance, that amount of distortion decreases. So all else being the same, the coherence area increases. Again, one can test the amount of spatial coherence in a given source of light by utilizing Young's double slit setup or experiment. If the deformation in the wavefronts changes from wavefront to wavefront, then interference pattern is not going to be stable. In fact, if these changes are kind of random, then interference pattern will completely disappear. Let's now briefly discuss some output characteristics of a source of light. I chose the pulse source, but we are going to extrapolate this to a continuous wave or a DC source as well. And so importantly, each source is going to be characterized by power output. In case of pulse sources, we will have pulse duration, pulse repetition period, and please note that for DC source, then pulse duration simply goes to infinity. We live in imperfect world, so all these quantities are going to experience jitter variations, which we can call, for example, noise or instability or some other appropriate terms. And so speaking about noise instability, for light sources, we generally talk about two types of noises or instabilities, short-term and long-term. So short-term will mean fractions of seconds, long-term may mean hours, minutes, hours, days. So the boundary between short and long is not that well defined. And there are a myriad of causes or reasons why we could have fluctuations. For example, on the short scale, we could have drifts due to power supplies driving the light sources. We could have fluctuations in how light is generated itself. There could be also rapidly changing environmental conditions like temperature or vibrations. The long-term stability is usually affected by aging, either of electronics that is driving the light source or the light source itself. So with this, we can now transition to our second part, where I'm going to briefly review, kind of high-level review of well-known broadband sources. So by these, we mean these are sources that produce polychromatic light. And so the standard bearer of such sources is the black body source. If I have an object of area A, temperature T, and that object is dense, it doesn't have to be actually solid, but if it's dense, sufficiently dense, then it's going to produce radiation whose spectral distribution, i.e. spectrum, is shown on the right-hand side, artist's conception, of course, and this is known as a black body distribution. And the equation above gives a black body spectrum devised by or discovered by Planck. So this is also known as Planck distribution. I should point some interesting aspects of this black body radiation. One is that the spectral radiance or the amplitude, or if I integrate this curve, the power will depend on not only the area of the source, but also on the temperature, in fact, temperature to the fourth power. So very steep dependence on temperature. And also the peak at which this distribution occurs, or the as we call it lambda max, is temperature dependent. So in other words, if I change the temperature of this black body, the spectrum is going to shift above horizontally and vertically. So there are some practical realizations of broadband sources that rely on this black body distribution, and one well-known is the quartz halogen tungsten filament lamp. And so it's the tungsten here that is going to be, as you can see here in the picture, is the element that thermally emits the radiation. So it's worth pointing out that these are indeed thermal sources. On the right-hand side, one can see the spectral irradiance, in this case, some distance away from the source, and is characterized by smooth distribution. Let us now go to a discharge tube. And so discharge tube contains some gas. What gas it is depends on specific application. There will be two electrodes and the voltage or current source. So the gas here is brought into a plasma state, so we create a little plasma region, and that plasma region is maintained electrically. So the electrons that are passing through are ionizing the atoms, and when the atoms recombine, they produce light. And so you can have various forms of recombination. Electrons can go from the free state, ionized state, to bound state, and that is the contribution to the continuum. We can also have a transitions, bound transitions, which give me the various peaks that we observe in this hypothetical spectrum. Now, there's quite a bit of interesting physics involved in discharge tubes. And by the way, this is quite relevant for our laser-driven light sources, as we'll see later. The question is, what gas should I use? What kind of geometry of electrodes should I use? Does it depend on pressure? What kind of voltage should I apply? And so some of these questions can be answered by Paschen's law, which shows here excitation voltage as a function of pressure times distance between electrodes product. And we have various plots for various gases. I should also point out that the shape of electrodes do matter as well, even though it's not explicitly made clear in this plot. So now that we are discussing discharge tubes, I would like to talk a little bit about some issues in this particular source. You may be wondering why I do that, because this source is actually most comparable to a laser-driven light source. And so more intimate comparison is perhaps due. So here we have a plasma arc between the two electrodes. As we said, this plasma arc is maintained by effectively electric field that exists between the electrodes. However, with time, the plasma arc can become unstable and can flicker, can move. Also, please note that the arc is not exactly circular. It has some geometry, could be quite actually complex. So why does instability arise in this source of light? So first we have the process known as sputtering, and so atoms of from which the electrons are made will be sputtered. In other words, they leave the surface and go wherever. Many of these atoms are going to end up on the glass, inner surface of the enclosing glass. So in effect, we get erosion and corrosion on the electrodes. And we also have deposition of the atoms on the inner glass. So that leads to darkening of the light output. So the source becomes dimmer with time, and the corrosion / erosion on the electrodes will distort the electric field and will effectively distort the shape of the plasma, leading to flickering or power variations from this source. Let's move on. Let's now move on to LED, light emitting diode, which is a PN junction using semiconductors that have so-called direct band gap semiconductors. Silicon is not direct band gap, so these materials are different than silicon. The direct band gap means that when there is an electron-hole recombination, a photon is emitted. LEDs are usually quite monochromatic, and that's because the light emitted depends on the band gap energy. So if I wanted to create a broadband, there are a number of ways of doing that. One is to combine a number of LEDs. So for example, if I combine BGR, I'm going to get, well, spectrum that consists of these features. And it turns out that the human eye would kind of interpret this as kind of whitish light. If I want a more accurate depiction of white light, another possibility is to coat typically a blue LED with phosphor, and that is going to give you a broader spectral distribution shown by the black curve on the right-hand side. Let us now look at a rather fascinating source of broadband, which is known as supercontinuum. This is a system actually that consists of a short pulsed laser, femtosecond laser, and a nonlinear optical fiber. So the lasers, or a laser, is going to produce nearly monochromatic pulse of light. However, when that pulse of light propagates in this nonlinear optical laser, incredibly, the spectral distribution broadens as shown artist's conception at the top, and more realistically at the bottom. And so we go from a pulse of monochromatic light effectively to a broadband distribution. Interestingly, the shape of the spectrum depends on the length of that nonlinear optical fiber. And so therefore, by varying the shape, or I'm sorry, the length of the fiber, one can change or modify the spectrum in a desired way. So these were broadband sources that we are all likely to be familiar with. And so if you're wondering what is the purpose of this webinar, the answer is that I would like to introduce a relatively new addition to the universe of broadband sources, namely laser-driven light source. So let us first have a first look, kind of bird's eye view of what this contraption is, and then we are going to have a more intricate look at what exactly happens inside of the bulb. So to produce a broadband source using laser, we have the following components. So we have a bulb, glass bulb, filled with gas, typically xenon, and this gas is under high pressure, typically 30 atmospheres or so. We do have electrodes. In addition, we have optics, which will take light from a continuous wave laser and focus that light somewhere in the central part of the bulb. As I'll discuss shortly, we are going to create in this system a small region of very hot plasma, 10 to 20,000 degrees Kelvin, which is actually hotter than the surface of the sun. This plume of plasma is going to be quite stable in position and power output. It's going to produce broad distribution of light, and also with very high power. In fact, the power output will be proportional to the power that is used in the laser. The wavelength of the laser, though not shown here, can be invisible. Actually, not visible, but typically in the IR, but not very deep IR region. So let's go through the steps of what's happening in the source. So first, ignition. So we said that we are going to use xenon. So first, xenon's ionization energy is actually quite high, about 12 electron volts. We already said that the laser used is kind of in IR, and so its photons or laser photons cannot directly ionize the xenon. And so therefore, in the first step, what we do is to use electrical circuitry to ignite a plasma arc. So we ignited plasma arc. Once we have that plasma arc, then we are going to shine light. So laser's light is going to be focused, and as we'll discuss shortly, it's going to maintain a small volume. Let's call this maybe focal volume of plasma. So in that focal volume, we find the following components. There will be neutral xenon, there is excited xenon, there is ionized xenon, there are excitation photons, i.e. those coming from the laser, and then we have emission photons. Please note that outside we have mostly neutral xenon. So now the ionization is maintained again only in the region which is shown by the yellow ellipse. On the right hand side, you see an image, the actual image of this light emitting region, and that gives you kind of an idea how small it is. So it's not circular, it's elongated, and about 60 by 150 microns for this particular light source product. I should also mention right away that G, gravitational field, will be in such a way that G will be pointing to the left. So if the laser light comes from left, G is pointing to the left. In other words, we shine light against the gravity. So orientation, geometrical orientation of the source does matter. And the reason for that is that if you were shining laser light from the side, then the light source would exhibit more instability. Okay, so there will be two processing taking place in this plasma. One is absorption of laser's energy, so let's call it pumping. And then there will be emission. So the competing process is emission, where atoms are going to lose light, emit light, and it is that light that we want. So currently, for a stable system, you have to have an equilibrium between pumping and emission. So let's look at details of the pumping. So remember, we already had existing arc, plasma arc. There were many xenon atoms in excited metastable states. Metastable means longer lived. It is from these states that electrons are going to be put into the free state, either in non-radiative manner, which means via collisions with electrons or other atoms, or radiative by absorption of radiation. This radiation could be from laser, preferably, but could also be photons that were produced by the competing emission process. However, most importantly, there will be also a process known as inverse Bremsstrahlung, where already free electrons are going to increase in energy by absorbing laser photons. This is in fact the main mechanism which keeps electron electrons hot. So a few things about inverse Bremsstrahlung. So if I had free electron and nothing else, and the photon comes in, that electron cannot completely absorb that photon. Yes, you could have competence scattering, where photon loses some of its energy, but you cannot have a complete absorption. However, if the electron is in the vicinity of a heavy ion, as shown here, this becomes now a three-body process. And in this case, this electron can absorb that photon. So now we have emission. And so there are various modes of emission. And remember, it is this emission that produces light that we are going to then siphon out from our laser-driven light source. So first, you have a free bound transitions. So electrons from ionized state are going to end up in bound states. Then you have bound to bound. So already bound electron can go to lower energy level. And again, importantly, you could have free to free transitions where higher energy electron will go to a lower energy state but still remain free. For example, when it slows down as a result of collision. And so this is now known as Bremsstrahlung. So again, as we said earlier, importantly, you must have an equilibrium between these two processes. If there is no equilibrium, if there is more emission than absorption, then the plasma is going to shrink and maybe extinguish. If you have more absorption than emission, the plasma region is going to expand until equilibrium is reached. So now it's time to compare spectra of some of the laser-driven light sources products that are produced by Energetic, which is the subsidiary of Hamamatsu, versus some other sources like tungsten, which is the black body source, deuterium lamp, or ordinary xenon arc lamp. And so the first thing to note right away is that laser-driven light source is very, very bright. Please note that this is a logarithmic scale on the y-axis that gives us spectral irradiance. Radiance. And so these sources, LDLS sources, are orders of magnitude brighter than the other broadband sources. Okay, so now let's compare some spectra for only LDLS sources. And I would like to point out one important feature of these sources, and that is its very wide spectral range. So the emission is from basically ultraviolet. It's not basically, it is ultraviolet, all the way to IR. Of course, there are different intensities. This particular source is brightest around 400 nanometers, but the spectral irradiances at these shorter and longer wavelengths are not negligible. Now, if you're wondering how do I get, say, this green curve, which is brighter than the blue curve, the answer is that it will be in the laser's power. It is the laser's power that is going to control how much light we get from that bubble of plasma, and it's also going to affect details of the spectrum. And so another subtle point to point out is that these wiggles that are clearly visible in the blue curve, which may be due, for example, to bound-bound transitions, kind of smooth out as the power of the laser increases. And that's most likely because you are more and more progressively more dominated by not bound and bound transitions, but free transitions, or maybe free bound transitions. Let's now look a little bit more at the practical design of laser-driven light source. These two pictures are actually kind of redundant and not really completely showing the practical design. But there are basically two sets, or there is a set of optics that is focusing the laser light onto the plasma bubble. And what's not shown, perhaps it should have been shown, is that we have another set of optics. In some designs, actually, that other collecting optics may be fused with focusing optics, but doesn't have to be. And so that we have a collecting optics, which will collect light from the plasma bubble and put it out for customers' use. As we'll see shortly, the great advantage is that because this is nearly a point source, one can then collimate the light, collected light, and pass it on to other parts of the optical system. So I would like to now summarize some of the properties of LDLS light. So first, it is a broadband spectrum spanning from UV to IR. Second, it does have high spatial coherence. And let's remember why, and that's because the source is small. So we have lots of light, but from very small volume. If you could shrink that volume to zero, then it would have infinite spatial coherence. But of course, the volume is not zero. So there is a finite but high spatial coherence. We have a low temporal coherence for the broad source because the spectrum is very broad. We have high brightness. So again, the amount of power that we get is high from that very small focal volume. The light is DC. Now we can understand why pulsating LDLS is difficult, because to pulsate LDLS, you would have to vary the laser's power, but that changes the property of the plasma. And so if pulsed light is necessary, it may have to be done, for example, using external choppers to create pulses of light. There will be short-term noise, and that short-term noise is dominated by the noise in the laser itself. There is long-term stability, and that long-term stability will be dominated by environmental conditions. So let's talk a little bit more about noise stability and the issue of background. So again, we are back to our glass bulb, plasma region in yellow. And here I showed that the laser light actually comes against the gravity. So what can happen? Well, many things can happen in this system. But first, let me point out that the pressure in the plasma is the same as pressure outside. If it were not the case, the plasma region would grow or shrink. Using ideal gas law, then we can deduce that the density is lower than outside because temperature is higher than outside. And so therefore, we have a gradient in density and temperature across the boundary between the plasma and the neutral gas outside. Such gradients can, for example, create a number of instabilities in the plasma. One of them known as Rayleigh-Taylor instability. We have diffusion, where plasma can diffuse into a region outside. We have buoyancy, since this part is hot and this one is hotter. And so there will be a tendency for this blob to move up. There could be acoustic waves created, which can then bounce in the glass. There could be refractive effects, since the index of refraction is likely to vary in the gas. There will be scattering of light, both laser and emitted light in the gas. There will be a refraction of that light and also scattering from the glass itself, and more. So there are many possible factors that you could worry about. So yes, we can worry about these things and ponder how important they are. But one approach is empirical approach, and to simply test the stability of the plasma region. And so in the next 2 slides, I'm going to show you some results of such stability tests. So in this slide, we see the location of center of mass of the plasma. So in other words, where is the center and how stable it is? So we can see that the center of mass of emission does move around a little bit. But if you look at the units, it is in micrometers. So the movement is on the order of 0.2 or so in both x and y directions, micrometers. So that gives you an idea of, effectively the geometrical flickering of the source. One can then conduct short-term fluctuation measurements. And so here we see a setup and peak-to-peak variation in the output power. And we see that for various scan times, observation periods ranging from 1 second to 40 seconds for different laser powers, we get peak-to-peak variation not exceeding 1%. You may be wondering, is it big? Is it small? Well, shortly we are going to see comparison with other sources. And we'll see that it's not the best, but it's also not the worst. It's actually very good and comparable to other sources. And here is an empirical plot showing long-term power output. And by long-term, we mean hours. In fact, this point here is 10,000 hours. And the plot shows that the output can decline by about 10% in the visible and a little bit higher decline in the UV part of the spectrum. So if I were to, if you were to ask me what is the typical lifetime of that bulb, then the answer would be around 10,000 hours or more. So before moving on to applications, I would like to stress one great advantage of this particular source of light, and that is that it's almost point-like. It's a point source. And so what it means is that you can more easily collimate it. So here's our point source of light. I bring a lens with a high numerical aperture because I want to collect as much light as possible. Remember, numerical aperture depends on the index of refraction in this region and also the sign of the angle, but that can be translated to focal length and diameter. But anyway, we need a high numerical aperture not to lose, not to waste light, and the light emerges collimated. Then I can focus that light again and pipe it into maybe a slit or a fiber or whatever system I have. And so if I have a point source of light, I have high throughput, high efficiency. Again, little loss of light. There will be always loss of light. You can never collect all the light, but it will be less loss than if the source is extended. If the source is extended, it is not possible to collimate the light. It is impossible, in fact, to collimate. And therefore, if you want light from this extended source to be then piped into a slit or fiber, there will be higher loss. So lower efficiency and lower throughput. So point-like source, high brightness, and broad spectrum are the 3 great advantages of laser-driven light source. So it's now time to compare our source to other sources. And so here is the sequence in increasing brightness. And so you can see that LDLS is brighter than all the sources on the left-hand side: deuterium lamp, tungsten, LED, xenon. The only source that competes in the brightness area is the supercontinuum. Okay, table. So these tables are very useful. Of course, I will not go over each entry in this table. This PowerPoint will be available to the attendees, and I highly encourage attendees to ponder them after the presentation. But the table contains some important considerations when selecting a source of light. Certainly price is one of them, lifetime, size of the source, output stability, and wavelength range. And so the price quickly makes, you can clearly see that the price for LDLS tends to be higher than other sources versus the only source that is comparable in price is supercontinuum. However, please note the other aspects like source size, lifetime, or wavelength range, especially wavelength range. It is LDLS that has, in fact, the greatest range, even greater than the supercontinuum, i.e., it can extend deeper into the UV part of the spectrum. So it is now time to discuss some applications of laser-driven light source. So let me actually begin by application that for which I don't have a slide. But I'll just describe it very quickly. So far what I discussed is LDLS, traditional LDLS that produces effectively white light. However, I could couple that traditional LDLS with a slit or monochromator, and the monochromator or the slit can be moved, and by that I can then create effectively a monochromatic source with the wavelength that you can adjust by the location of the slit. And so we call such a product tunable light source. In other words, you can tune the wavelength of the output light by specifying the location of the slit. Now, the other application, which actually is the device that EQ also offers, is known as the chromatic spectral engine. And this is a very fascinating application of our LDLS. So basically, it consists of light from LDLS, and we have some diffraction element. In this drawing here, it's in the transmission mode, but it could be in the reflection mode. Anyway, we are going to create a spectrum somewhere, and at the location of the spectrum, I have arrangement of mirrors who or which can be controlled electronically. In other words, they can be turned on or off. In other words, they can be turned between reflective and non-reflective mode. And because of that, I can reflect, say, desired wavelengths and collect these wavelengths in some collection optics. And so what this allows me to do is to actually produce a source of light with a desired user-specified spectral composition. In other words, suppose I want some green, some red, some UV, and a little bit of IR with desired amplitudes, and I can create that light with this particular engine. So as we said, you can control the wavelength, but you can also control amplitude. And the simple picture of that is that I have mirrors or sequence of mirrors, and again, when I flip them between on and off, I can select various wavelengths, but for a given wavelength, I can flip more than one or two, and so that will control the intensity of light for that particular wavelength. So you can model not only spectral composition, but also intensities of the various components. Of course, there are limitations. Maybe the webinar is not the most efficient time or medium to talk about these limitations, but in principle, one can construct light with desired characteristics. So before I list some particular applications, I would like to bring to your attention another table, a long table, where on left-hand side we have various general applications. Many of them are in life sciences, but not necessarily. And then in the second column, we have currently used sources of light for that application. And then the next few columns, we have the various constraints for that application. For example, is brightness required high or low? Is the numerical aperture output high or low? Tunability, modulation, stability, long life, and cause. So in the last column, we have our view or our estimate whether LDLS is suitable for that application or not so suitable. Just to make it very blunt, it would be kind of crazy for me to replace incandescent light bulb that illuminates my room with LDLS source, right? For a variety of reasons. So this is obvious no. But there may be situations where such replacement is highly desirable, and others where it's a more subtle choice. Of course, we are happy to work with anyone and help to make the appropriate assessment. But now let's go to some applications of laser-driven light source and tunable light source as shown here. So one very common application is in testing devices, for example, CCDs, photodiodes or PMTs, whatnot. I could have an array of them. And because my source is very bright, and also because I can control the wavelength emitted with the tunable light source, I can then study things like quantum efficiency, uniformity, and other aspects of detectors' performance and characteristics. Another interesting application of broadband light source is spectroscopic lipsometry. This is a field where we are going to study, for example, thin films and be interested, for example, in their thickness or how dielectric constant changes, or maybe looking at dielectric tensor, which means variations in the dielectric constant x, y, and z. And so what one does is one measures the reflectance as a function of polarization. Unfortunately, these measurements directly do not give you the quantities that you are looking for. You must create model of the sample, and then the model is fit, or what one compares the model with the measurements. If there's a disagreement, then one changes the model until there is a reasonable agreement. Another interesting application which utilizes the very short coherence length of broadband source is this white light interferometry. This is basically a 2D version of optical coherence tomography. I have a target here whose topography I would like to study, the shape of the surface, or maybe some features in the close to the surface. Right. So this could be biological tissue or some other maybe man-made material. Okay, so what it consists, of course, is a broadband light source because, again, its coherence length is short. We have a movable mirror, and we have a beam splitter and the camera. And so what one does, one changes the location of the mirror and records the images. These images together form so-called correlogram. And from that correlogram, one can determine topography of the target. So again, this is very similar to kind of point-by-point optical coherence tomography, often used to study, for example, structure in a human eye. Another interesting application is astronomy. Before any serious observations, CCD or image sensor needs to be calibrated, and so this calibration is known as flat fielding. One can use the sky itself, so that just after sunset or just before sunrise, one can point telescope at the blank sky and obtain so-called sky flats. But sometimes in the heat of observations, this may not be convenient or not possible, so one can then utilize so-called dome flats. A dome flat is the surface that is equally or illuminated, so flat illumination. And so the LDLS, because again of its very high power and because it can be easily collimated, makes possible to perform such flat fielding efficiently. In addition, if the telescope is used for spectroscopy, the CCD or the spectroscopic tools need to be calibrated as well, which means one needs to have a stable spectroscopic source. And so one can then use the chromatic engine to artificially, in some sense, create a spectrum which then can be used for the calibration. We have very little time left, but this is my last slide. And so, as we said earlier, this source of light produces UV light. We also remember from physics that how well you can discern detail depends on the wavelength of light used for illumination. And so, for example, if I want to look at structure on a cellular level, one desires light of shorter wavelength. And so this allows measurements as shown on the slide, where we are obtaining both image and spectrum. So this is a very hot these days, hyperspectral imaging, hyperspectral interferometry. So again, this is the fine detail which one can study these samples is due again to availability of shorter wavelength light from our broadband source. So with this, I would like to thank everyone for listening to this presentation. Below is my contact information. If you would like to obtain slides, please make the request with the Photonics Spectra, and that will happily provide the slides to anyone interested. So again, I thank everyone for attending.
Thank you very much. We do have time to take a few questions now before we close. Everyone, if you have not already, please go ahead and type your questions and comments into the webinar chat. All right, so my first question is the output of the LDLS adjustable?
Right, so that depends. So remember, we pretty much discussed three possible designs, right? Three possible products. And so what I called like ordinary laser-driven light source, the output cannot be easily changed internally, because to do that, we would have to change the laser power, and that will change the property of the plasma. However, externally, one can vary the output. One can use neutral density filters, for example, or if one wants a pulsed light, then one can use choppers to do that as well. Now, in case of a tunable light source, remember that is just the ordinary LDLS working together with a slit monochromator. And so there we can certainly vary both the wavelength and the intensity as well. And finally, for the chromatic engine, yes, we can both vary the amplitude of light at a given wavelength, and we can certainly select the wavelengths. And so basically, one types in what one desires, and the system is going to produce that light on a very short time scale, I should say. So it takes really order of milliseconds for that light source to be realized.
Perfect, thank you. I think we'll do one more question. This last one is,
Okay.
what applications can the chromatic spectral engine be used for?
So that's right. So let's remember that this chromatic spectral engine allows you to create light with the spectral composition that you desire. So therefore, can be used for any type of characterization where spectrum matters. So, for example, if I want to characterize, let's say CCD, how it responds for certain wavelength, then I could, with this engine, create that wavelength and use for the measurement. We could again use it for calibrating telescopic observations. So any type of calibration, sensor calibration, which is wavelength dependent.
Thank you very much. And everyone, if we did not answer your question already, please look out for a reply from us later. If you do think of another question or would like to request a copy of today's slides, you can let us know by emailing webinar@photonics.com. That's webinar@photonics.com. And just one final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive a link to that recording in your email inbox. I'd like to thank Dr. Slavomir Piatek one last time and thank all of you for participating today. This webinar was presented by Hamamatsu Corporation and hosted by Photonics Media. Thank you, everybody.
Thank you.